Hello students, I am Saranya Babu, Assistant Professor, Department of Computer Science and Machinery, AJIET Institute of Engineering and Technology in Mangalore. So today we will be discussing the last chapter that comes under Module 5 of Big Data Analytics, that is Social Network Analysis. Okay, so this is the last chapter that comes under this fifth module, that is Module 5. That is the chapter name is Social Network Analysis. Okay. So first we will, so in this particular chapter we are going to discuss, we'll see the concepts of social networks and social network analysis, and we'll see what are the applications of this social network analysis. Social network analysis is shortly called as SNA. Okay, it is also called as, it is shortly called as SNA, and then we'll see the different topologies that comes under this. And also we'll identify the techniques and algorithm for discovering the subnetworks. And we'll see the concept of Dept page, and we'll see about the page rank and how it is used, okay, how it is computed, and we'll see the differences between social network analysis and data mining. So starting from the introduction, what is social network analysis? We'll see what is social network analysis. Social network analysis, or SNA, are a graphical representation of relationships among people or entities. Okay, let it be people or let it be entities. SNA stands for the graphical representation of relationship. Fine. So SNA is the art and science of discovering patterns of interaction and influence within the participants in a network. So what this SNA, social network analysis, is shortly called as SNA. So it says that it is the art and science of discovering. It tries to discover patterns of interaction and influence within the participants. These participants can be either some entities or it can be people. Fine. They're trying to find the patterns of interaction and the influence within this participants in a network. Fine. So that's what I said, within the participants in a network. Now these participants, when you're telling that it is a participants, these participants can be people, they can be organizations, they can be machines, concepts, or any other kinds of entities. Okay, you're just trying to find out the pattern of interaction among these things. So an ideal application of social network analysis will always discover what the characteristics of network, including what are the central nodes, what are the subnet, what is the subnet structure, and when you take subnetworks, they are clusters of nodes where the within subnet connections are stronger than the connection with the nodes outside the subnetwork. Right? So now how this SNA is accomplished is like by using this graphically representation. Clear? Using this graphical representation. So SNA is accomplished through graphically representing social relationships into a network of nodes and links, and apply iterative computational techniques. So that to measure, if you want to measure the strength of relationship, you can make use of this. You can apply iterative computational techniques so that you can measure the strength of relationship between the entities that you are considering. Fine. So now we will move on to the applications of social network analysis. Coming to the applications of social network analysis, the applications are, first one is self-awareness. Okay, so self-awareness means when you are visualizing our social network, okay, maybe either ours or this or her social network, they can help a person organize their relationships and they can support the network. Yeah? So self-awareness, it gives a self-awareness. So when you visualize that social network, it will help you to organize the relationships and support the network. So that is why it is given as the application is self-awareness. Next is communities. Fine. Communities mean the social network analysis can help identification, construction, and strengthening of networks within communities to build wellness, comfort, and resilience. Clear? So what the SNAs can do, they can help in identifying, constructing, and strengthening. Okay, they will do identification of network, construction of network, and also strengthening of network within communities for what? To build wellness, comfort, and resilience. Clear? So now next application that comes under application of SNA is marketing. Okay, next is marketing. So there is a popular network insight that any two people are related to each other through at most 7 degrees of links. Here there is a popular network insight. Insight means a feature or a view that they got, that any two people, if you take any two people, they are related to each other through at most, at the max, 7 degrees of links. So organization can use this insight to reach out with their message to large number of people, and also they can listen active to the opinions. Here they can also listen actively to the leaders which will give correct opinions, and also they can understand their customers' needs and behaviors. Clear? So there is a popular network insight. What they have got is that if any two people are related to each other, they are related through at most 7 degrees of link. So this particular insight will help the organization. How? So that they can reach out their message to large number of people. Okay, and also they can listen to the active leaders who gives opinions, and also they can understand the customers' needs and the behaviors and their complaints. So next is public health. The next application is of public health. So public health means, suppose if when you have the awareness of networks, they can help identify the paths that certain diseases take to spread. So public health professionals can isolate and contain diseases before they expand to other networks. Clear? So this again, social network analysis, they can help in identifying the paths. Suppose if there is any continuous diseases, or if there is any containment areas and all. So if they can identify the paths that certain diseases that take to spread. So what happens when they know that this type of disease is getting spreaded, they can isolate those areas. Clear? And so that it will stop from spreading. Fine. So these are the 4 applications of social network analysis. First one is self-awareness, then communities, then marketing, and then public health. Fine. So these are the applications of social network analysis. So now moving on to the next topic, that is network topologies. Okay. Now we'll see there are 2 primary types of network topology. Anyhow, this is a graphical representation, right? Social network analysis. So we need to say what are the different types of networks that we have. So first we will see which are the different types of network topologies. So here there are 2 primary types of network topology. We will see which are those 2 primary types of network topology. Then one is ring type. Clear? One is ring type, and another one is hub spoke topologies. Clear? One is ring type and another one is hub spoke technology. These are the 2 primary types of network topologies. One is ring type and another one is hub spoke topologies. Clear? Now each of the topologies, they have different characteristics and benefits. Clear? They have their own characteristics and they have their own benefits as well. Fine. We'll see each one. Which is the first type? The first type that we have is the ring network. Clear? The first type that we have is ring network. So in the ring network, nodes typically connect to their adjacent nodes in the network. So what happens in ring network? You already know all these network topologies, right? So how the nodes are connected in ring topology or in ring network? Nodes are connected to their adjacent nodes. Clear? They are connected to the adjacent nodes. So potentially all nodes can be connected to each other. Clear? It can be connected to each other. Now a ring network could be dense, where every node has a direct connection with practically every node. If that is the case, normally the ring network need not get connected to all, one node need not connected one node need not get connected to all the other nodes. But normally one node gets connected to their adjacent nodes. That is how normally the ring network forms. But in case if the network or if the node, they have a direct connection with almost every node, then the ring network could be dense. Clear? So ring network could be dense where every node has a direct connection with practically every node. Clear? When they have a direct connection with practically every node. Now, a dense network with more connections will allow many direct connections between pairs of nodes. Understood? So now once again I will tell a ring network could be dense, right? If a dense means every node has a direct connection. Or it could be sparse. Sparse means what? Where every node connects to a small subset of the node. So the number of connections needed to reach from one node to another could vary tremendously, right? Because if it is a dense network, it will be in that case. If it is a sparse network, it will be in another way. So the number of connections from one node to another node could be vary. So a dense network with more connection will allow many direct connections between pairs of nodes. That's what I said. Clear here? So see here in the previous point also I said, if a ring network, if every node has a direct connection with every node, then it is going to be dense. Clear? So they are telling a dense network with more connections will allow many direct connections between pairs of nodes. Yeah, correct. Because dense means when a network becomes dense, when each node has a connection between other nodes. So obviously, in a dense network with more connection will allow many direct connections between pairs of nodes. Okay. Now, in a sparse network, one may need to traverse many connections to reach the desired destination because the connections will be limited. It doesn't connect with every other nodes. Clear? It doesn't connect to every other node. So, what happens is, in a sparse network, one may need to traverse many connections. Clear? It may have to travel through many connections so that it can reach the desired destination. Now, okay. Now, in the one more example, if I can give, see if I take a peer-to-peer email, okay, or just consider an example of messaging. Okay, so a peer-to-peer email network or a messaging network, it is an example actually on the ring model. So, as anyone can potentially directly connect with anyone else, correct, right? Peer-to-peer means I am messaging to one person like that, a direct connection. So, in practice, the email networks are sparse as people connect directly with only a subset of people, not with from that dense is very rare. Clear? So, that is what an example that you can give for the ring network. So, what and all we had learned in ring network? So, anyhow, these are the two types. One is ring network and one is hub spoke. So, in ring network, nodes typically connect to their adjacent nodes. Fine. Typically, what happens is one node gets connected to their adjacent nodes, but potentially, so potentially all nodes can be connected to each other. Now, in case if the ring network, if it is dense, that means where every node has a direct connection with practically every node. Okay, a ring network could be dense where every node has a direct connection with practically every node. Then this ring network could be dense. Clear? It could be dense. So, a dense network with more connections will allow many direct connections between pairs of nodes. Okay. So, dense network with more connections will allow many direct connections between pairs of nodes. So, in a sparse network, one may need to traverse many connections to reach the desired destination. So, in order to reach a desired destination, in case if it is a sparse network, okay, in case if it is a sparse network, then it might take a lot of time because we know that the connections are limited. Clear? The connections are going to be limited. Fine. So, now let's see the next type, that is, which is the next step? It is hub spoke model. So, what is there in hub spoke model? What is the thing in hub spoke model? See, there is one central hub node in hub spoke model. Fine. In the hub spoke model, there is one central hub node to which all the other nodes are connected. Is it clear? There is a central node. Okay, there is one central node to which all the other nodes are connected. Fine. which all the other nodes are connected. So there are no direct relationship between the nodes. Is there any direct relationships between the nodes? It is understood that it is clear that when they said that there is a central node and every other nodes are connected to this central node means it is understood that there is no direct connection between all the nodes. Clear? It is understood. So now there are no direct direction between the nodes. So nodes connect with each other through which one? Obviously through the hub node. Clear? Nodes connect the nodes connects with each other. The nodes connects with each other through the hub node. Understood? If we get a doubt, okay, how this nodes are connected? The nodes are connected with each other through the hub node. Is it clear? So there is a hierarchical network structure since the hub node. Okay, so there is a hierarchical structure since the hub node is central to the network. Okay, since it is central to the network. Okay, so once again I'll tell in the hub spoke model. Clear? In the hub spoke model, there is one central hub node. Understood? So towards that central hub node, all the nodes are connected. Right? All the nodes are connected to that central hub node. So what happens is there is no direct relationship between the nodes. Fine? There are no direct relationship between the nodes. So what happens? The nodes connect with each other. So how these nodes are connected? Nodes are connected with each other through the hub node. Hub node means the central one, the connecting node. So this is a hierarchical network structure since the hub node is central to the network. So this particular network structure is a hierarchical one since the hub node is central to the network. So the hub node, okay, when you take this hub node, the hub node is structurally more important because it is central to all the communication, right, between all the nodes. It acts as the central. Okay, so it is like a central to all communication. Now the good thing about the hub spoke network is that one could predictably reach from any node to any other node through traversing exactly just two connections. Correct, right? Because all the nodes are connected to the central node. So see that node A and node B is connected through the hub node. So if I want to reach from node A to B, I am clear that A to hub node to B. So only two connections I have to traverse. Suppose see A, B, C, D, all the four are connected to the hub node. If I want to traverse from A to D, it is clear that I need to traverse from A to hub node to D. Understood? So the good thing about this hub spoke network is that we can predict it. We can clearly predict that the reachability from any node to any other node. Okay, the ones which are connected in the hub node. The reachability from one node to another node is traversing exactly just two connections. Only two connections I have to travel. So that is why I have given the example when A, B, C, D are connected to the hub node. If I want to traverse from A to D, A to C or anywhere, I need to go from A to hub node and hub node to the next node. That's it. So I can clearly predict that only two connections are required to traverse. That predictability is clear in the hub spoke network. So as an example, suppose if you take modern airlines and all. So they operate on this model to maintain the hub networks from which they operate flights to a large number of airports. That is one example which we can give. So this is about the hub spoke model. So in ring model, we had one node is exactly connected to the adjacent nodes. Hub spoke model means all the nodes are connected to the central node, hub node. So one good thing about the hub spoke model is that when you want to go from one node to another node, you are very clear that only two connections I need to traverse, then it is going to be easy. Okay. Now we'll see another way of analyzing networks. Okay, which is another way of analyzing networks. So another way of analyzing network is to define the centrality or the importance of every node. Another way of analyzing networks is to define the centrality or the importance of every node. So how will you see that? The number of links associated with a node, clear? The number of links associated with a node is a sign of centrality of the node. How many links are associated with a node? How many links are associated with each node? So if you take that, it is going to be a sign of centrality of the node. Fine. So what we are taking, this is another way of analyzing network. So we are going to analyze a network by defining centrality of every node. Every node you are taking. Centrality, or also you can call it as importance of every node. How will you see the importance of every node? The number of links associated with a node. Okay, how many links are associated with a node is a sign of centrality of the node. Clear? The number of links associated with a node is a sign of centrality of the node. How many links are connected to one node? That will give you the centrality of the node. How many links are connected? Clear? So in the ring network, in the figure below, each node has exactly 2 links. Thus, there is no central node. However, in the hub-spoke network, hub node N has 8 links, while all other nodes have only 1 link. So the node N has higher centrality. I tell you, this is the example of ring network. Okay, this is the example for ring network. This is the example for hub-spoke network. Clear? So in the ring network, you take each node. Okay, I will take the node A. Okay. Tell me how many links are there from A to H and from A to B. So the importance of node A is 2. What about node H? Connection to A and connection to G. Importance is 2. So every node in this network is having equal importance. That is importance 2. Okay, only 2 links. So importance is that. What about hub-spoke? In hub-spoke network, you know that node A is having only 1 link. Clear? Node A is having only 1 link. Node B is also having only 1 link. Node C is also having only 1 link. Now, node D, if you take, node D is also having only 1 link. Node E is having only 1 link. F, 1 link. G, 1 link. What about node N? How many links does this node N has? Node N means this is the hub node. Central hub node is node N. Tell me how many links the central hub node has. Central hub node has node N to B. So 1, 2, 3, 4, 5, 6, 7, 8. 8 links are there from central node N. Is it clear? So from central node N, you have 8 links. Is it clear? From the central node N, you have 8 links. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 links are there from the central node N. Fine. So now, that is what you mean by centrality of the node or the importance of the node. That's what it was given. In the ring network, there is no central node. Each node has exactly 2 links. Correct, right? Each node has exactly 2 links. There is no central node. So now, however, in the hub-spoke network, the next one, that is, this is the hub-spoke network. In hub-spoke network, the hub node N has 8 links, but all other nodes have only 1 link. So, N has high centrality. This one is going to have the highest centrality or highest importance. Clear? So, one more thing is, a variant. Suppose if you have a variant that combines both the above types, okay, the one which is going to combine both the above types is the network of networks, in which each participating network will network will connect with other networks at selected points of contact. The one which is having the both the type. Okay. So if you take an internet and all is a network of networks. Fine. So next topic that which we are going to see is the techniques and algorithms. Clear? Next topic which we are going to see is techniques and algorithm. Okay. Now there are two major levels of social network analysis. Clear? There are two major levels of social network analysis. One is discovering subnetworks within the network. Discovering subnetworks within the network. Next is ranking the nodes to find more important nodes or hubs. Okay, one is discovering subnetworks within the network. Next is ranking the nodes to find more important nodes or hubs. Okay, these are the two levels of social network analysis. We'll see each one in detail. So first is what? Discovering subnetwork, right? Finding subnetwork within the network. So how will you find the subnetwork? Finding subnetworks. Okay, how will you find the subnetwork? A large network could be better analyzed and managed if it can be seen as an interconnected set of distinct subnetworks, each with its own distinct identity and unique characteristics. So what they are telling is how you can find subnetwork is, suppose if in case you have a large network, try to analyze that large network as an interconnected set of distinct subnetwork, okay, a group of subnetwork. When you get a large network, you try to find the subnetworks, large number of subnetworks, so that different subnetworks are there, they are interconnected. So it can be seen as an interconnected set of distinct subnetworks, each having its own distinct identity and also they have their own unique characteristics. Clear? With its own distinct identity and unique characteristics. So you need to find out, when you get a large network, you try to find out the distinct subnetwork. Okay, try to analyze as a distinct subnetwork, so that each subnetwork will have its own identity and also they will have their unique characteristics. Fine. So this is like doing a cluster analysis of nodes. Okay, it is like just like finding the cluster analysis, because what we are doing, maybe we'll see, okay, the networks that are the nodes which are grouped together close by, they will be grouped into one subnetwork. The other one which are nearby, they will be grouped into another subnetwork. So it is a kind of cluster analysis, right? This is like doing cluster analysis. So nodes with strong ties between them would belong to the same subnetwork. Same tie means the connection that which you are having, then they will fall into same subnetwork, while those with weak or no ties, they will belong to separate subnetwork. So this is unsupervised learning technique, as in this one, I mean that algorithm called as a priori algorithm. There is no correct number of subnetworks in the network. So we'll see and show you the. So I'll show you the example diagram for that. Okay. This, see here. This is one subnetwork. This is another subnetwork. This is one. This is one. This is one. So like this, a network with distinct subnetworks has been identified. Here, a network with distinct subnetworks has been identified. So now, next is what? So when you see that this representation, right? So visual representation will help you to identify the subnetwork. So that is why we have used different colors. So they can help differentiate the types of nodes. So representing strong ties with thicker or border lines, you can see there, can help visually stronger relationship. Like that, okay? With the stronger relationship and the weaker relationship, you can do this kind of distinction. Fine, you can find the way how you can distinct the networks within each other. Now, next is how we are going to compute the importance of nodes. Clear? How we are going to compute the importance of nodes. How you have to compute the importance of nodes. So, when the here what we are going to see is how we are going to find the importance of the nodes. Okay. So when the connections between the nodes in the network, when they has a direction to them, okay, when you have different nodes, so when the connection between the nodes in the network, they have a direction, they'll have a direction to them. So then the nodes can be compared for their relative influence or rank, okay. So then the connection, then the nodes are there, connections between the nodes. the network has a direction to them. Clear? So then the nodes can be compared, so that the nodes can be compared for their influence or rank. Clear? So now these terms that importance, influence, rank, they'll be used interchangeably, okay, for the purpose of that. When we talk, this rank, influence, importance, everything is going to be like it will be used common, fine. So this particular thing is done using the influence flow model. Clear? This is done using the influence flow model. Fine. So when the connections between the nodes in the network has a direction to them, when they has a direction to them, then the nodes can be compared for their relative influence or rank. So this is how this is done. This is done using the influence flow model. Fine. This is done by using influence flow model. So every one outbound link from a node can be considered an outflow of influence. Clear? Outbound link from a node, they will be considered as an outflow of influence. Same way, every incoming link. Okay, suppose there is incoming link. Every incoming link is similarly an inflow of influence. Okay, outbound link will be the outflow of influence, whereas incoming link will be the inflow of influence. Clear? Outbound link will be the outflow of influence. The incoming link will be the inflow of influence. So here that is done. Now when you are computing, so there will be many direct and indirect flows of influence, right, between any nodes in the network. If we take any nodes in the network, there could be any number of influence in the sense how they are connected based on that. So now computing the relative influence of each node. Okay, when you are computing the relative influence of each node, it is done on the basis of an input-output matrix of flows of influence among the nodes. Okay, how they are computing the relative influence of each node? When they are computing the relative influence of each node, it is done on the basis of an input-output matrix. Clear? It is done on the basis of an input-output matrix of flows of influence among the nodes. Okay, it is done among the nodes. So assume each node has an influence value. Okay, think that each node has a influence value. So the computational task is to identify a set of rank values that satisfies the set of links between the nodes. Okay, so the computation, what is the computational task that we have? The computational task is to identify a rank values. Okay, rank values are the importance values or the influence values which satisfy the set of link between the nodes. So, and whenever you are doing, it is going to be an iterative task where we begin with some initial values and we will continue to iterate till the rank values stabilize. Clear? So, this is a computation that which we are going to perform. So, how we are going to compute is, it is done on the basis of an input-output matrix. Clear? It is done on the basis of an input-output matrix. Clear? Input-output matrix. So, it is done on the basis of an input-output matrix of flows of influence among the nodes. So, assume that each node has a influence value. Fine? They have an influence value. So, the computation task that we are having is to identify a set of ranked values that satisfy the set of links between the nodes. Clear? Set of links between the nodes. So, it is an iterative task where we begin with some initial values. Okay, we will start with some starting values and we will continue to work on it. We will continue to iterate till the rank values, whatever rank values you have, till the rank values get stabilized. Clear? Till the rank values stabilize, you keep on doing it. The iterations will keep on doing based on that matrix. Okay, so until the rank values are stabilized once. So now we will see one example. Consider the following simple network. It has 4 nodes. Okay, which are the 4 nodes? A, B, C and D. Okay, A, B, C and D. and 6 directed links between them. Okay, 6 directed links between them. What are the direction? A to B, B to A to C. Okay, which is the direct connection from A? Node A links into B. Okay, now if I take node B links into C, node C links into D, node D links into A. This is a normal connection that we have. Then again, node A links into C and node B links into A. So how many connections are there? 1, 2, 3, 4, 5, 6. Understood? And note that there is a bidirectional okay. So when we are considering the simple network, we have 4 nodes there. Understood? We have 4 nodes, that is A to B, B to C, C to D, D to A to C, and B to A. So which is the as I said, note that there is a bidirectional link. Which is a bidirectional link that we have? A to B and B to A. Clear? So there is a bidirectional link. Node A links into B and node B links into A. It is there in both the direction, A to B and B to A. So that is the bidirectional link. So we have specified the links based on this figure. And what is the goal that we have? The goal that we have is to find the relative importance or rank of every node in the network. Clear? We need to find the importance. We need to find the importance, influence, or also you can call it as rank, okay, of every node in the network. Okay. So we begin by assigning the values for influence or rank, okay, for each node. For the node A, rank is RA, node B, RB, RE, RD. The goal is to find the relative values of these variables. Now there are 2 outbound links from node A to node B and C. Okay, there is 2 outbound links from A to B is there and A to C is also there. Okay, again there are 2 outbound links from node B to node C and A. See that diagram. Node A has 2 outbound links, correct? Understood. There are 2 outbound links from node A. Which are the 2 outbound links from node A? One is A to B and one is A to C. Now then again, so both B and C, when there is an outbound link from node A to B and C, this both B and C, okay, both B and C are going to receive half of node A's influence. Why? Because there are 2 outbound links, right? From node A to B also is there, from node A to C is also there. So B and C is going to receive only half of node A's influence. Okay, it is going to receive only half of node A's influence. So similarly, there are 2 outbound links from node B. Okay, which is the other node that is having 2 links, 2 outbound links, node B. To which one? From node B to A and B to C. So again, both A and C are going to receive only half of the influence of node B. Okay. So always remember, now see the diagram. Node A has 2 outbound links, 1, 2. To which one? B and C. So both B and C are going to get only half of node A's influence. Okay. Half to B and half to C. Now again there are 2 outbound links from node B. B to A and B to C. So again now node B is going to send 2 outbound links to A and C, right? So A is going to get half of node B's influence and node C is also going to get only half of node B's influence. Clear? Understood? A is going to get half of node B's influence. C is also getting half of node B's influence. That is what we need to see here. The influence, when that matrix, when we are preparing, we need to know this. Fine. And then tell me for the other nodes. What about node D? There is only one outbound link to node A. So thus node A gets all the influence of node D. Complete influence of node D will be received by A because there is only one outbound link to node A. So node A will receive 100% of node B's influence. Correct? So what about node C? Node C also has only one outbound link, right? C also node C to D. There is only one outbound link from node C. So node D is also going to receive 100% of node C's influence. Clear? Understood? So D will get all the influence. D will get all the influence of C. Similarly, A will get all the influence of D. Fine. So now we will make the formulas. We need to find out the rank. So rank, see this, why this RA is equal to 0.5 into RB plus RD. What did I tell? See that diagram. A is going to receive half influence of node B, right? Whatever B has rank, okay, rank and influence is same. So whatever rank B has, its half will be received by A. So that is why half means 0.5. So that is why when I am calculating the rank of A, RA is equal to 0.5. That means why it is 0.5? Because node B has two outbound links. Are you getting it? Node B is having two outbound links. Which are the two outbound links node B is having? One is this one and one more is this one. So this particular RA is going to get half of node B. Clear? So that is why RA is equal to, when I am calculating rank of A, rank of A has got half of the rank of B through this one. So 0.5 into RB plus this D's. Okay. This is a complete one, right? This is a complete link. Fine. Complete means D has only one link, that is to A. So obviously A is going to get complete rank of B. So that is why RA is equal to 0.5 into RB. Why? Because there are two links from B. So it is divided halfway. So 0.5 into RB plus complete RB. Okay. That is why it is come as 0.5 into RB plus RD. So node B gets, next I am calculating the rank of node B. Okay, I am going to calculate the rank of node B. So how will I calculate the rank of node B? How will you see the rank of node BC? I am going to calculate the rank of node B. So check what are the incoming links to node B. Okay, what are the incoming links to node B? What are the incoming links to node B? One is this one. Right, only one link, only one incoming link it has. Correct? Only one incoming link it has. That is A. Correct? But A has two outbound links, so it is only 0.5 into RA. Okay, node B is receiving only half rank of node A, and there is no other incoming links to node B. So it is half into RA. Clear? So that is why it is given as 0.5 into RA. Is it clear? That is what is given as 0.5 into RA. Now you check node C. Node C. Which are the incoming nodes? Incoming links to node C. So node C is having two incoming links. Correct? Node C is having two incoming links. Which are those? One is this one, and one more is this one. So is it half or is it full? From node B there were two links. Correct? From node B there are two links. So C is going to get only half of half of what? Half of the rank of So node C is going to get one incoming link from B and there is another incoming link from C. But when incoming from B, you need to check, is there any other link from B? Yes, B to A is there. So obviously C is going to get only 0.5. Okay, 0.5 of which one? 0.5 of node B. Correct? 0.5 of node B is received by C. What about A? A also has two links. So even This also C is going to get only 0.5. Is it clear? C is also getting only 0.5. So it is like RC is equal to 0.5 into RA plus 0.5 into RB, because C is getting, but when C is getting, you should check from where the link is coming. From B the link is coming, correct? From B we are getting the link, but B has already given one link to A, so only half of B's rank will be given to C. Same way from A the C is receiving rank from A, but that time also A has already given another half to B. So again C is getting only half of the rank of A. So that is why rank of C is calculated as it is not RE, it is RC. Okay, it is RC. It is not RE. It is RC. Okay, it is RC. Okay, thus RC is equal to 0.5 into RA plus 0.5 into RB. Clear? Now next RD. See, wherever E comes, node D. Node D gets all the influence of node C. Correct? When you check node D, this node D has only one incoming link. Correct? Node D is having only one incoming link, that is from C. Whether C has any outgoing link? No, only to D. So complete rank of C will be given to D. So how it will come? RD is equal to, it will be given as RD is equal to RC. Okay, RD is equal to RC. Fine. RD is equal to RC. Fine. So we got RA, RB, RC, RD. All the four nodes we have got. Understood? Here wherever I have written this also, it is not E, it is C. Okay. It is C. Okay. Now we have four equations using four variables. How is that? Four equations using four variables. How will you find this four equations using four variables? See this. RA is having RB's 0.5 and RD's 1. Correct? So RA is having RB's 0.5 and RD's complete 1. There is nothing from RA, nothing from RC. Now when I take RB is having only 0.5 of RA. Okay, RB is having only 0.5 of RA. Other things are 0. There is no rank from other ones. Next, RC has 0.5 of RA plus 0.5 of RB. From RA and RB 0.5 each. So RC is having from RA 0.5, from RB 0.5. Others it is 0. What about RD? RD, rank of D is completely equal to rank of C. So RD from RA nothing is there, RB nothing is there, but RC complete is there. 1. Understood? Again RD it is 0. So understood? So this is how you are going to make the matrix. So first you need to form this equations by checking which are the incoming links to that node. Check whether that incoming links are divided into half or 3, 4, 3. Again 3 links are there, means again you have to divide like that. You need to find out. So now one can start with any initial rank values. You can start with any starting rank values you can put by yourself by keeping 1 by n or 1 by n means here we can take it as 1 by 4. Okay. So the 1 by n you can take it as 1 by 4 because n is 4 here, right? Number of nodes are 4, A, B, C, D. So 1 by 4 means it is going to be 0.25, 0.25, 0.25, 0.25, 0.25. Now what you have to do is you have to compute the revised values using the equation stated earlier. What is that? Because RA's value has been changed, right? Again make use of these equations and change it. Clear? You will get new set of values. We will get a revised set of values shown as iteration 1. Clear? You will get a revised set of values in iteration 1 because RA has some value. So when you put it, you substitute RA that 0.25 here, 0.5 into 0.25, So what RB will get 0.125 like that. Understood? You have to put the values. When RC's value, see, RA is 0.5 into RB. Now what is the rank of RB? Initial rank we don't know, right? That's why we have put RB and RD here. But initial rank values, I am going to put it as 1 by n. 1 by n means 1 by total number of nodes. How many nodes are there? A, B, C, D. So 1 by 4 means initially all the nodes rank will be 0.25. Okay. Now substitute those values in each of these equations. So RA is equal to 0.5 into 0.25 plus 0.25. How much it will come? We'll see in that iteration 1. It will come to 0.375. Next, RB again. RB is equal to 0.5 into 0.25. Clear? So 0.5 into 0.25. You will get it as 0.125. Okay. So next, RC. RC is equal to 0.5 into 0.25 plus 0.5 into 0.25. How much you will get? You will get it as 0.250. Understood? Again, RD is same that of RC. So it is 0.250. So this is how you get iteration 1. So this now what is the new values for RA, RP, RC, RD? Which are the latest values of each of the rank? 0.375, 0.125, 0.25 and 0.25. So this is ignored. Now this values will be considered. Again do the next iteration. Next iteration means substitute these values. Okay, substitute this point now. RA value is 0.375, RB is 0.125, RC is 0.25, RD is 0.25. Substitute in this equation. Clear? Substitute in these equation and find out what is the next iteration 2 value. So iteration 2 values you will get when you are substituting it in those equations. You will get the next iteration values. Clear? So next iteration values you might get it as RA is so much, RB is so much, RC is so much, RD is so much. Now for the next iteration you will consider these values. You will substitute in that equations, that is RA, RB, RC, RD. When you calculate you will get this set of values. Understood how we are doing? So working from values of iteration 2 we can do few more iteration till the value stabilize. Okay, until you get a stabilized value. Here we have shown iteration 8, 0.33, 0.167, 0.250, 0.250. Further there is no much change means you can stop it there. Clear? So the final rank shows that rank of node A is at highest at 0.33. Thus the most important node will be A. The lowest rank is 0.167, that is for B. So RB rank, node B is the least important node, and node C and D are the middle one. So which is the highest node? Highest important node is A, and the B is the least important node. C and D comes in the middle. Is it clear? Actually this problem is very easy. When any set of node is given, see here, when any set of node is given, try to calculate the equations for each rank. Okay, rank of A. When you calculate the rank of A, you check how many incoming links it has. First you note down all the links. Okay, and check for each node how many outbound links it has. Like this you make a list. And then you have to frame this equation. So how will you frame the equations for node A? Suppose for node A, if you want to frame the equation to calculate the rank of A, you check how many incoming link it has. How many incoming link it has? One is from node B and one is from node D. So from node B, if I take, already it has 2 outgoing links. Clear? So obviously A is going to get only half of node B. Clear? Half rank of B. And what about node D? D doesn't have any other outgoing link. D has given its complete rank to A. So A will get complete rank of D. So RA, rank of A, can be written as 0.5 into rank of B plus rank of D. That is how I have written 0.5 into RB plus RD. Similarly, you calculate the rank of B, C and D. Fine. So initially you don't know the values of all these variables, right? We have just put the equation for each rank. How to calculate each rank? I have made the equations, but I don't know how to put the values for that. So what we are doing is, initially we are taking the values and form this matrix. Clear? Before that, form this matrix. How will you form the matrix? You check for RA which all node has given its rank. B's 0.5 is there, D's complete 1 is there. So when you take RA 0, from RB it has got 0.5, RC nothing it has got, from RD 1 it has got. Now RB has got 0.5 of RA. So RB when you take, RA is 0.5 you have got, RB 0, RC 0, RD is 0. Clear? Like this you have to form this matrix. After that, initially you can put the value for these variables as 1 by total number of nodes. How many nodes are there here? 1, 2, 3, 4. So 1 by n means 1 by 4. 1 by 4 will get. So 1 by 4 means 0.25. Put 0.25 for all the variables. Substitute these values in these equations. So when you substitute RB, RD 0.25, RA 0.25, RA 0.25, RB 0.25, RC 0.25, when you do, you will get the new set of value. That is iteration 1. Now, the recent rank values are these. So instead of 0.25, now you consider this one. RA value is 0.375, 0.125, 0.25, 0.25. Again, substitute in these equations and find iteration 2. Okay. Now, when iteration 2 is done, substitute these values instead of the previous one. Okay, doing those equations. Like that, continue until there is no much change. Okay, until you get a stabilized value. Further, there is no much change. So, until you get a stabilized value, you can do this. Clear? So, that is what you do for such problem. So, when you get a stabilized rank, you can see in this which is having the highest value. Which is having the highest value? RA. Node A is having the highest value, that is 0.33. So rank of node A is highest. So the most important node is A and the lowest rank is 0.167. It was of B. So RB is having the lowest rank, that is 0.167, and B is the least important node. And finally node C and D are the middle one, are in the middle. Node C and node D are in the middle. Okay, so that is how you have to find out the importance of node. Fine. That is the problem. Normally when they ask the problem, you can solve it. It is very easy. Okay, we can find which is the highest ranked node. Okay. Now coming to the next topic, that is page rank. Okay, in order to find the page rank. Now page rank is a particular application of the social network analysis techniques about to compute. We have already seen the page rank in the previous videos, right? What do you mean by page rank? We have seen all those concepts. So here also we are going to just see what is this page rank. Okay, so page rank is a particular application of the social network analysis techniques about to compute the relative importance of websites. Understood? That is how the page rank, the one which is having the highest number of links, will be ranked high. I have said in the previous videos. So that is why. So it is just to when you give the search, the pages how they are listed is based on the ranks. So they were about to compute the relative importance of websites in the overall World Wide Web. So every web page is a node in a social network. Clear? When you consider a social network, every web page is a node. And all the hyperlinks from that page become directed links to other web pages. Fine. Now, every outbound link from a page, means the one which is going to refer to another page, is considered as an outflow of influence of that page. Okay, outbound link. Now, an iterative computational technique is applied to compute a relative importance to each page, and that score is called as page rank. Is it clear? So every web page in a social network is considered as a node, and all the hyperlinks from that page will become directed links to other web pages. We know that when you click on that web page, it moves to another page, right? We know that from one page it moves to another web page. So every outbound link from a web page is considered an outflow of influence of that web page. So an iterative computational technique is applied to compute a relative importance to each page. Fine. So that score is called as the page rank. Is it clear? That score is called as the page rank. Fine. Now when you take the practical considerations in this SNA, see the network size. So most SNA research is done using small network. Okay? When you perform research and all, most of the social network analysis, they are done using small networks. So collecting data about large network is very challenging, right? So they do it on a small network. So this is because the number of links is the order of the square of the number of nodes. Okay, that is one consideration, that is network size. Next one is gathering data. Okay, gathering data. So electronic communication records like email, chats and all, they can be used to gather the data easily. And the data on the nature and quality of relationships need to be collected using survey documents. How is the data valid and the quality of those relations and all, you can understand by making some survey documents. So capturing and cleansing and organizing the data, it will take a lot of time and effort. So that is another consideration, that is gathering data. You will get the data from all those social networks and all, but the thing is cleaning the data, gathering the data, cleaning the data and preparing for the analysis is going to be little time consuming. Then comes the third one is computation and visualization. So modeling large network can be computationally, it will be challenging, and also visualizing them also we have to will require some skills. So big data analytic tools and all may be needed so that we can compute the large network. And the last consideration that we have is dynamic networks. Okay, the last one is the dynamic network. So dynamic network means when you take the relationship between the nodes in a social network, they can be fluid. So they can change in strength, they can change in the functional nature. For example, when you take, there could be multiple relationship between two people. So they could simultaneously be co-workers, co-authors, or they could be spouses, right? So that is what the dynamic networks issue also. So these are the practical consideration when you are doing research in terms of SNA. One is network size, gathering the data, computation and visualization, and then dynamic networks. Clear? So then the last one which we have is a comparison between social network analysis and the traditional data mining, okay, or the traditional data analytics. So in terms of nature of learning, social network analysis is unsupervised learning, data mining is supervised and unsupervised learning. Analysis goals, okay, how do you analyze it using hub node? You will try to find out the important node, and you will try to find out subnetwork, right? Those are the two techniques that we use. First we need to find a subnetwork, then we need to find the importance of nodes. In traditional data mining, decision rules, cluster centroids and all those things are being used. Next, data set structure. Data structure for SNA, what structure you are using? Graph of nodes, right? You are making use of graph of nodes. Clear? Graph of nodes and links. Coming to data mining, it is rectangular data of variables and instances. Coming to analysis technique, visualization with statistics, iterative graphical computation, then machine learning statistics for data mining. Quality measurement, this is usefulness of key criterion, this is predictive accuracy for classification technique. So these are the differences. So overall, SNA is a powerful method of analyze. You can analyze the relationship between the entities. Entities can be anything, okay? So that you can identify some patterns out of it. So there could be subnetworks in a network based on strong ties. So how we know, how we have calculated the importance of node, how we calculate the rank of node, then how this page rank is implemented and all those things. Fine. So you can refer this particular topic in your notes. This is the last chapter that comes as 5.5 in your notes which I've already shared with you. Okay. Thank you for listening.